A very good morning to all of you here. I'm Aparna Prabhakar, Vice President at IBM. I'm responsible for development, growth, and delivery of quantum ecosystem for IBM. And to begin with, let me tell you what our journey has been so far. In May 2016, IBM Quantum put the first quantum computer on cloud. And it is my true belief that that actually accelerated the pace of adoption of quantum computing as technology. And the numbers really speak for themselves. Today, we have a fleet of over 20 systems which are available to our partners to use. We have 410,000 users, 180 members in our IBM Quantum Network who are doing 3.5 billion executions per day. From day one, it has been about just one thing for us: adoption, adoption, adoption. And that is clearly evident from this exponential growth we have seen in adoption. In May 2022, we had 1.6 trillion lifetime executions on actual IBM systems. Think about that, 1.6 trillion executions. We have come a long way since we put that first quantum computer on cloud. And this is in part possible due to 180 members we have. Out of 1,500 plus papers which have been written on research being done on IBM system, 870 of them are by our partners. And these partners come in various shapes and sizes. They are hubs, they are academics, they are research institutes, and they are startups and GSIs. Stefan Erlington, who leads the startup global program for us, will be speaking tomorrow morning. I won't take time to go in depth today, but if you're interested in what we're doing with startups, I would highly encourage you to attend that. But let's not forget about our strategic partners. These are partners we've chosen to partner in a big way. We are working with them to really push the boundary of research, industry, and workforce development. University of Tokyo is extremely central to us. Kei Kawase, who leads the IBM Quantum at Japan, will talk about it later in this talk. And Japan's success is success for IBM. Now, if you look at future, as a community, it's extremely important for us to get to quantum advantage, to really craft that path towards quantum advantage and unlock the value, like Matt just before me indicated, will unlock billions of dollars. Now, let me just start with saying quantum is confusing. At one end, you have NISQ, where there is a near-term push to actually do something what you can get away with noise on the systems. And at the other end is, hey, we can't do anything without fault tolerance. And let me not forget Inspired, which essentially is really pushing the boundary of classical computing till quantum advantage gets through. And this is a gap. It's broken. There is no bridge from one end to another. Does that mean we are in limbo? And the answer is not really. We have to craft. We have to use practical methods which exist today, like error mitigation, which can fix and which can make a continuous path to that future. So the path to quantum advantage has to be continuous. Now, if you're listening to me, you're asking, okay, Aparna, this is all great. Tell me how do I get there? And we at IBM are really doing this by thinking about quantum circuit, which is a fundamental unit for compute on quantum computing. And we are asking two primary questions. The first question is, how do we map interesting problems to quantum circuits? And the second question is now, how can I make sure that these quantum circuits run faster on quantum computer than they run on classical? I'll tackle each of these questions separately. Let's talk about the first one. We know we cannot do this alone. We cannot answer the first question alone. And this is where IBM is bringing its network into place. We are deliberately partnering and engaging with industry experts to identify, to look at the problems which are classically hard to solve and really go deeper on that quantum end. And we've built this into our complete strategy. Now, I'm going to make a statement here. We at IBM believe we can make money on quantum computing. This should not surprise anybody. But what we've done is we've chosen to focus really deeply. And what we are really doing is we've decided that we will provide Qiskit runtime services, which is powered by quantum systems, to really bring compute to our clients and partners. Outside of this, we are creating libraries and tools and bringing some consulting to our industry. But we are partnering on those fronts. We are partnering with GSIs, we are partnering with startups, ISVs, research institute, really being thoughtful about how we are bringing these tools, capabilities, application spaces to this space. And from day one, I'll say this again, it's been about adoption, it's been about partnerships. And this philosophy which we have goes into everything, even the science we are doing. So if you look at our scientific papers, they are not about application domain. They are about building capabilities on quantum. We are in the business of building capabilities, providing tools so that quantum is moving ahead. And this is evident by 60+ application areas which our partners are working on with us today. And you can see a whole variety of them. And just going a level deeper, this is just a subset of our industry partners who are working with us. Rudy is going to talk about Q, which you see on far left over there. They're doing a tremendous job with how they're engaging the industry. And Rudy, who's a part of IBM Quantum, will be speaking tomorrow in depth about what are the application areas, but I won't go in deep on that. What I will do is take an example of Woodside. Woodside is one of our active partners, and they most recently published how to use quantum machine learning for a large set of data more efficiently by estimating kernels based on small data sampling using structures and data. Now, what does that mean? It pretty much means that quantum circuits are scalable representations of chemistry, material, and high-energy physics problems, which is pretty exciting. So we are moving forward on this. Now, remember what I said. We are in the business of providing capabilities. And that is really evident in our relationship with the US government. We are working across Department of Energy and Department of Defense. And we are providing them with quantum computing as a tool. We are working with them to actually build out what does serverless really mean? What does quantum circuit cutting look like? Really focus on defining the tools which is needed to get to that next level of quantum advantage. Now, to build those tools, you have to get to the second question. And how do you chart a path to develop quantum technology that can enable circuits that run faster? I would say that's through IBM roadmap. But before I go there, let's look at historical data. Now, I love this chart, but let me just walk you through this. On the x-axis is the complexity of quantum circuit, which is defined by both the width and the depth of the quantum circuit. On the y-axis is the simulation cost, which is defined by the time and scale of your computation. Now, it's really well known that classical generally scales exponentially. But we are beyond that with 60 qubits on cloud. Like today, we have 127 qubits on cloud. And really, to get to error correction and to make it useful, you need a couple of things. You need really, really, really a lot of qubits. You need excellent error correcting code. And let's be honest, that's far, far, far away. So, what does that actually mean? Now, the error mitigation curve over here, you're going to look at it and you're going to say, hey, Aparna, wait a minute. You just spoke about error mitigation being the answer, but that's exponential in nature as well. What's going on here? Is all hope lost? We cannot get to quantum advantage? Is that what you're telling me? And I would say, look at the curve. Look at that crossover point. And there is a point, if you get low enough error and you get fast enough circuit, there are going to be use cases which are going to be quantum advantage. So you see that crossover point between classical and white color curve? That's where you have good quantum volume, quality, and you have good speed. And we believe that's less than a year or two away, the first unlock happening. We do. And this is where this whole trinity of metrics comes into play. And that's why we have been talking so much about why the metrics make sense. And that trinity of metrics is three things. Every time you ask a quantum computing company about, hey, what are you building? How are you thinking about it? Ask them about these three things. What is your scale? What is the quantum what is your quality? Which is, what's your quantum volume? What's your operational error? How do you think about it? And then finally, what is the speed? If you're extremely slow, it takes you forever. You're not going to be able to do much with quantum computer. If there is one thing you want to take away from this talk of mine, this is what I want you to take away. That is the path to quantum advantage will be driven by improvements in quality and speed of quantum systems as their scale grows to tackle increasingly complex circuits. And we have really adopted this into our roadmap. And I love it when IBM does not show the roadmap and our partners show the roadmap. You saw Kyo-san actually show the roadmap. And here's what we are doing here. So we released in April 2022 the expanded roadmap. Till today, we've been able to deliver everything which we have said on the roadmap to the date. Now, what we've done with the hardware, if you look at our hardware at the bottom, you will see that we are able to deliver with the current architecture, Osprey and Condor, and that is reducing the error rates. It's going to deliver on the quality. And then with Heron, we are getting a completely new architecture for the chip, which is the 133 qubits there. And as you move forward, we are introducing concepts like quantum communication, inter-chip connection, classical communications. And by the time Kookaburra, which is a Japanese bird, which is an Australian bird, I apologize for that, comes in, it's actually combining all of this together, and it allows us eventually to scale to hundreds of thousands of qubits in future, which is a big deal for us. And because we've been able to connect this classical and quantum communications together, it allows us to go to that next level up and really think about threaded primitives, error mitigation techniques, etc., which really advances the technology. Now, what are we also doing in this advanced roadmap differently? We are coming from top. We are saying, hey, you are those classical users. When you think about your paradigm, when you think about CPU and GPU, think about QPU. And think about how your orchestrations happen at that level. So we're building tools like intelligent orchestration, circuit knitting, others, and also creating prototypes hand in hand. And that is what we are bringing to Japan. Now, I'm cheating a little bit, and I'm going to ask my Kei Kawase to come and talk to you a little bit in the last few minutes we have about exactly what we are doing in Japan and how all of this ties together.
Thank you, Aparna. Kawase でございます。
This is Kawase speaking. I would like to give you an idea about how we've been developing our partner. Aparna talked about the importance of our partner's ecosystem as she was talking. Now, in Japan, we actually are running frontier activities on that. We are working with the Keio University. Back in 2018, we have created Hub. First time ever inside IBM globally. We have launched that. Back then, 4 private companies and Keio University and IBM formed this partnership launching this hub. And after that, if you look below that, University of Tokyo and us back in 2021 had formed this. And a contract was signed back in 2020. If you look at the left-hand side, you see the actual hardware in Shinkasaki City. We have built that so that our partner ecosystem partners can have direct exclusive access to that. The one in the middle, it is quantum computer hardware test center. So commercial, there is no such thing as commercially available quantum computers. So there were no companies who are producing components that are exclusively for quantum computing. So they were using for other applications. For example, electric wave telescope. We are using technology from different areas to make quantum computing. But as we have more concentrated qubits, we have to have exclusively designed product parts, components for quantum computing, which we would like to closely work with the Japanese manufacturers to make next generational quantum computing parts. Quantum computing's usage adoption rate is actually growing quite fast in Japan. Almost new machines are getting close to 100% in terms of the usage. Right now, we have 11 industry members, organizations in this endeavor. There are 40 research papers being published. IBM and colleges have made the 7 sponsored researches working with academia. And IBM has that direct engagement that is like there are counts of 2. And so under this ecosystem, we have material science, AI/data science, as well as financial applications. And there are a few examples that were in 11. My colleague will be presenting to you tomorrow. Now, moving forward, IBM will be building the new world of quantum computing. So quantum computing will be center, working closely with classical computers, solving problems of the real world. And that's what we are working on right now. This is all available on YouTube. Please take a look at the clips on YouTube.
Vision for what we hope to do with Japan. We hope that it will become one of the first superconducting supercomputer center for quantum. And I would like to thank the Q2B team, the organizers, and everybody and the fellow speakers who've given us, Kay and I, an opportunity to speak to you about what we are doing here. Thank you.
Thank you.